Hello, my name is Tom Howard, and in this presentation, I, along with Ariana Moore, will share with you our Johns Hopkins University Environmental Health and Engineering Senior Design Project, Stormwater Management at the Fort Meade Motor Pool. We would like to begin by acknowledging the contributions of our two other project team members, Bormate Punrakwang Brahim and Marcos Pascual, who are not participating in this recording for the WEF Student Design Competition. We would also like to dedicate this project in memory of the late Dr. Ed Bauer, one of our professors who passed in the beginning of our senior design course, whose hard work and devotion to senior design at Johns Hopkins has enabled past, current, and future students to accrue relevant environmental engineering design experience. Fort George G. Meade is a 5,067-acre military installation located in Anne Arundel County, Maryland, as shown on the map to the right. The objective of our project was to design stormwater BMPs and impervious area removal strategies for the 8400 motor pool at Fort Meade. This aerial image shows an outline of where the 8400 motor pool is on the installation. As the fort maintains a network of conveyances that carry and discharge stormwater for a population under 100,000, Fort Meade is a small municipal separate storm sewer systems permit holder. The fort's MS4 permit was granted under the National Pollutant Discharge Elimination System and was intended to reduce and eliminate pollution resulting from rainfall runoff emanating from Fort Meade. As Fort Meade is located in the Chesapeake Bay watershed, it must adhere to Maryland Department of Environment's framework to meet the Chesapeake Bay total maximum daily loads for nitrogen, phosphorus, and sediment, which were established in 2010 after President Obama signed Executive Order 13508, prioritizing the Chesapeake Bay's restoration and protection. In order to meet these TMDLs, Maryland added an impervious area treatment requirement in which MS4 permit holders must treat and or reduce 20% of untreated impervious surface as of the permit holder's 2002 baseline. This goal can be accomplished by constructing stormwater best management practices for impervious area credits and is the principle that underlies our senior design project. Of several potential project sites identified by our professional partners at Fort Meade, our senior design team chose to design BMPs for the 10.1-acre Building 8400 motor pool. The motor pool is managed and operated by the National Security Agency, whose headquarters are on Fort Meade. As a result, the senior design team has a dual client, Fort Meade, the legally responsible MS4 permit holder, and NSA, the occupying tenant. The site is mostly impervious surface and consists of 3 parking lots, 3 buildings, and 5 carports under which vehicles can be parked. Water and electrical utilities exist mainly along the site's edge. Currently, the only stormwater practice on the site is a riprap ditch with stormwater drain inlets that act as a conveyance system along the western edge of the site. The site has 30 feet of topographic relief and 2 natural drainage areas, with the highest elevation of 170 feet in the southeastern corner of the property and the lowest elevation of 140 feet in the northwestern corner of the site. The site is comprised of Type A and Type D soils. The current state of the site is that there is no treatment of stormwater. The riprap ditch on the western border of the site is in poor condition and merely provides some conveyance to a storm drain network on the northwest corner of the site. Additionally, the concrete jersey barriers shown do not contain the flows, allowing overflow to flood downslope. The discharge of the 10-year 24-hour storm is 51.17 cubic feet per second currently. The riprap ditch is only able to convey a fraction of this flow. Consequently, the building's areas downslope of the site are often flooded during storm events, causing leaks and endangering electrical boxes. However, allocating funds to improve the stormwater management of the site can not only dramatically improve these issues with water quality, but also improve the quality of runoff entering Fort Meade's surface waters and help the client achieve its MS4 retrofit requirements. Before deciding on a final set of treatment alternatives for our site, we considered several BMP options, keeping in mind the physical constraints of the site and the needs of the client. These practices included infiltration trenches, grass swales, disconnection of rain runoff, bioretention practices, rain gardens, dry wells, and sand filters. Other practices such as permeable pavement, green roofs, and wet or dry ponds were excluded on the basis of client preference, sizing, and general applicability criteria. To evaluate the general performance of each potential BMP that could be included on the site, we constructed a decision matrix on the bases of upfront cost, maintenance, quality control, quantity control, aesthetics, and BMP lifespan as defined in our report. Criteria weights for each of these factors were based on the needs and preferences of the client. Quality and quantity control, along with maintenance, were given the highest criteria weights of 25% to reflect the client's preferences. The Chesapeake Bay program's Chesapeake Assessment Scenario Tool, which has estimates for nutrient removal, capital costs, operations and maintenance costs, and lifespan of each BMP, was referenced to determine decision matrix values for each BMP. Using this tool, we saw that in general, infiltration trenches offer the highest quality control, swales are the cheapest structural practice in terms of capital costs, and bioretention and rain gardens have the lowest maintenance costs. This slide shows the results of the decision matrix. The higher the score, the better. The interpretation of these scores is that wherever there is a proposed location for a BMP, of all of the possible BMTs that could be implemented at that location, the one with the highest weighted score should be built. A higher score is reflective of low upfront and maintenance cost, high quality and quantity control, appealing aesthetics, and long lifespan. Among the considered BMPs, infiltration trench is the highest ranked. Although some practices performed well in the decision matrix, they did not become incorporated when alternative designs were devised. For example, while rooftop runoff disconnections scored highly according to the decision matrix, they are limited by the amount of impervious surface in the vicinity of the site and the capacity of each downspout. Using the results of this decision matrix, we considered an alternative analysis and developed 3 alternatives for our client to choose from. The first alternative is to replace the existing riprap ditch that runs along the western boundary of the site with infiltration trenches, as shown in the map. In this case, the drainage area to BMPA is approximately 7.6 acres, and the drainage area to BMPB is approximately 2.1 acres. The peak discharges to BMPA and BMPB for the 10-year 24-hour storm as calculated using TR55 and the calculated reduced curve numbers are shown. A trench drain connected to BMPB is installed at the entrance to the parking lot to capture the flow that currently runs off to the building's downslope of the site. Note that BMPB extends into the existing road by approximately 8 feet to accommodate its receiving flows. We decided to extend the BMPB into the road as opposed to the parking lot because The first alternative is to replace the existing riprap ditch that runs along the western boundary of the site with infiltration trenches, as shown in the map. In this case, the drainage area to BMPA is approximately 7.6 acres, and the drainage area to BMPB is approximately 2.1 acres. The peak discharges to BMPA and BMPB for the 10-year 24-hour storm, as calculated using TR55 and the computed reduced curve numbers, are shown. A trench drain connected to BMPB is installed at the entrance to the parking lot to capture the flow that currently runs off to the building's downslope of the site. Note that BMPB extends into the existing road by approximately 8 feet to accommodate its receiving flows. We decided to extend the BMPB into the road as opposed to the parking lot because this portion of the road is a dead end. Doing so allows all existing parking to remain intact. In this alternative, infiltration trenches are designed to have rectangular cross-sections 8 feet deep by 20 feet wide at BMPA and 8 feet deep by 28 feet wide at BMPB. Although it does not fully meet requirements for environmental site design at BMPA, this alternative captures much of the site runoff without compromising site functionality, as no parking spaces are removed. This alternative, however, does not break up any of the sheet flow, which could increase the frequency and magnitude of erosion, clogging, and maintenance required for the pre-treatment sedimentation basins and infiltration trenches. The second alternative seeks to meet the environmental site design volume. To do this, the width of BMPA is extended by 36 feet into the RV lot as detailed by the map. As before, infiltration trench cross-sections would be designed to be rectangular to maximize volume detention. Under this alternative, the drainage areas remain almost the same as they were in Alternative 1. However, by expanding the trench in this manner, the nearest row of RV parking, a total of 14 spaces, would be removed, possibly compromising the site's functionality. Additionally, in this alternative, we assume the entirety of BMPA is an infiltration trench without pretreatment. To achieve the necessary pretreatment, additional area would need to be excavated within the fenced lot. Building within the lot introduces multiple issues, such as removing parking spaces and increasing construction costs associated with relocating fencing. The third alternative is to install the infiltration trenches as described in Alternative 1, but with an added trench drain that delivers runoff from the upper portion of the fenced parking lot to another infiltration trench, BMPC. In this case, the drainage areas and peak discharges to BMPA, B, and C are reduced as shown in the table. Note that the northern trench drain extends until it reaches the fenced portion of the upper lot. The northern trench drain does not need to be extended along the fence because BMPB is sized to accommodate the flows of the additional contributing area not captured by the new trench drain. Inclusion of the new trench drain breaks up the sheet flow being received by BMPA. This allows BMPA to be sized correctly according to MDE guidelines, that is, having a drainage area of approximately 5 acres. The new trench drain conveys flows to BMPC. Flows are pre-treated in a sedimentation basin before entering an infiltration trench. An underdrain conveys the flows to the existing storm drain network. 3 parking spaces in the RV parking lot have to be removed to properly size BMPC. Ariana Moore will now go into more detail about our design assumptions, cost estimation, and schedule.
We attempted to size each proposed BMP to meet the Environmental Site Design Volume, ESDV, as suggested by MDE. The ESDV is given by the equation shown, where PE in inches is the target depth of rainfall treated by the practice, RV is the dimensionless runoff coefficient, and A is the drainage area of the watershed that will drain to the BMP. The volumetric runoff coefficient, RV, is based on percent impervious cover at the site and is calculated using the second equation shown. The target PE value is based on the soil composition of the drainage area. The maximum target PE value is 2.6 inches. However, at minimum, the BMPs had to capture and treat the water quality volume, WQV, which is equivalent to 1 inch of rainfall. MDE requires that 25% of the WQV for infiltration trenches be pre-treated. This pre-treatment allows for sediments and other particles to settle out before entering the infiltration trench to prevent clogging and increase the lifespan of the practice. We designed sedimentation basins with rectangular cross-sections, riprap flooring, and a length-to-width ratio of 2:1 to slow down water and provide stability. For determining the dimensions of the infiltration trench, we first determined the maximum allowable depth of trench, Dmax. MD regulations allow a maximum storage time of 48 hours, and we assumed a porosity N of 0.4, as is typical of infiltration trenches. Based on the soil type, we assumed an infiltration rate F of 1.02 inches per hour. Once the depth of the aggregate in the trench is known, we could calculate the minimum surface area required for each trench to make sure that all of our infiltration trenches met the area requirement. In the infiltration trench design, there are several layers. From top to bottom, we have a 9-inch layer of cobble, a 6-inch sand filter, 4 inches of pea gravel, 8 feet of wash bank run gravel aggregate, and a 6-inch sand filter. The sand filters and aggregate layer were designed to satisfy MDE's 3 practice requirements. Beneath the sand filter, there's an underdrain system. An observation well is also placed near the trench's longitudinal center. For 2 of our BMPs, we use trench drains to help route water flows to the sedimentation basins and infiltration trench. We use the rational method to estimate peak discharge for the drainage areas. The peak discharge was used to calculate the open area needed for the trench drains grates. We treated the grate as an orifice for sake of calculation. We then used Manning's equation to determine the pipe dimensions required to accommodate the peak discharge. We propose using polyester glass fiber reinforced polymer concrete trenches with stainless steel frames and concrete anchoring. The bottom slope of the installed trench drains were designed to be between 0.5% and 1%, and the materials chosen were all load class C or higher to allow commercial vehicles, including buses, to drive over the trench without actually fracturing them. This slide illustrates what BMPA will look like in plan view. Flows from the fenced NSA parking lots will be directed into BMPA. Upon reaching the BMP, flows are conveyed by curbs into a pair of sedimentation basins, sedimentation basin A1 and A2. Both basins are sized at 60 feet long and 20 feet wide. Both infiltration trenches are sized at 180 feet long and 20 feet wide. BMPA is situated on top of two existing stormwater inlets, so we designed the outlet structure to be above these inlets. That way, overflows will drop right into the stormwater network and be conveyed off-site. This slide illustrates what BMPB will look like in plan view. Flows from parking lot upslope of BMPB will enter a sedimentation basin via a curb system and a 44-foot trench drain. The trench drain has a depth of 1 foot and a width of 8 inches. Without the trench drain, about 65% of BMPB's drainage area would bypass our proposed designs and continue to flood the buildings below the site. The basin is 14 feet wide by 28 feet long. The infiltration trench is 28 feet wide and 81 feet long. A major difference between BMPA and BMPB is that BMPB is not constructed on top of an existing stormwater inlet. Therefore, we designed the underdrain and outlet structure discharged to the left. That is actually north on the aerial image, and it would convey flows towards BMPA and will outlet into the existing stormwater network. BMPC is located on the northern border of the site. The BMP's drainage area was designed by our team to reduce flows to BMPA. We decided the best way to reduce flows was by using a trench drain to capture flows from the upper part of the site. The design calls for a 348-foot trench drain, and it conveys flows into the sedimentation basin. The trench drain to BMPC has a pipe width of 10 inches and pipe depth of 16 inches. The sedimentation basin is 8 feet wide by 25 feet long. The infiltration trench is 75 feet wide by 95 feet long. It extends into the RV parking lot, so 3 parking spaces will have to be removed. The cross-sectional area of infiltration trench C is typical of the general design we showed. However, the underdrain pipes will not outlet to the same place as the other BMPs. The underdrain pipes will convey flows north and tie in with the existing stormwater network up there. The rainfall depth actually treated must be back calculated based off of the given design. For infiltration practices, the ESDV is the porosity of the gravel media times the volume of the gravel aggregate. Once the rainfall depth treated is known, you can determine the impervious area credits achieved. For PE values over 1 inch, the impervious area credit relationship is not 1-to-1. Instead, it works like a step function after every 0.4 inch treated. MD also provides percent removal rates for sediments, phosphorus, and nitrogen based on the rainfall treated. These rates are also nonlinear. For BMPA, we had the opportunity to make the BMP larger without removing any parking spots, but the BMP would not have treated 1.8 inches, meaning the impervious area credits for the BMP would not increase, even though the BMP would be more expensive. BMPC was placed in an area that had more RV parking spots that could be removed, but we downsized the facility to the maximum rainfall depth treatment of 2.6 inches. While BMPB is the lowest credit achieving BMP, we decided to include it within our proposed design in order to treat as much of the water coming off of the motor pool as we could. Otherwise, the southern parking lot would not have any water quality treatment as the site condition is currently. A detailed cost estimate was created for our proposal. The budget cost estimate was broken into labor and material costs for each BMP. Within labor costs, equipment costs were added if relevant. Pricing data came from RS means and various local company price estimates. When pricing values conflicted, the estimates from Maryland suppliers were used. In addition to pricing out as many of the components for each BMP as required, we estimated an excavation amount and its associated price. As recommended by the client, a 20% upcharge was also added for complexity. Within the budget estimate, we did not include delivery fees or charges for offloading of materials. The budget estimate is for upfront costs only. It should be noted that the BMPC is the most expensive. However, BMPA is able to be profitable only because BMPC is present to minimize the drainage area of BMPA. We divide up the work schedule into 4 parts: pre-construction initial control measures, BMP construction and final stabilization, and landscaping and final inspections. A full Gantt chart of our work schedule is provided in our report. During pre-construction, we must first confirm the final design with the client. Other tasks that must be accomplished include developing protocols for the construction project, including control measures. We allocate 3 weeks for pre-construction. Initial control measures include installing erosion and sediment control, stormwater management, and waste and debris storage. Then, site clearing operations can begin, including clearing out the riprap ditch and stabilizing the disturbed area. We expect initial control measures to take 2 weeks. By the start of the 6th week, we expect to begin actual construction of the BMPs. At the end of the construction phase, an initial BMP inspection can be conducted. The construction process is expected to take 6 weeks. In the final steps, temporary controls will be removed and any disturbed areas will be stabilized. After final inspections and BMP testing is conducted, a notice of termination will be provided. In all, the project is expected to take 13 weeks to complete. We'd like to thank all of our professional partners and Hopkins faculty members as listed here for their assistance in making this project a reality. Thank you for your time.